Okay, folks, we're ready to start the next part of this GPS class, this GPS seminar. And today what we're going to talk about, or in this section what we're going to talk about, is using GPS data with remote sensing data. And specifically we want to talk about some of the challenges of integrating state-of-the-art geotechnologies into rangeland research as an example, but specifically using remote sensing data. A little bit of background here. First of all, there's a lot of geospatial research today that makes use of remote sensing data. But not all of it. You have to realize that in some cases you could have a strictly geographic information systems project where you're going to use your GPS to map features and never integrate or never utilize remote sensing data. Okay? But specifically there's some little nuances or I guess things that you need to know about when you are going to be using remotely sensed data. In a nutshell here, imagery is acquired. Whatever imagery that is, you have to acquire that data, purchase it from a vendor, download it, whatever it happens to be, georectify that data or georegister that data, and this can be done with the use of GPS. Okay, you can georegister using GPS data, and then field targets are acquired as a standard process, and we typically call those things training sites. Again, most most training sites are acquired today using GPS data. And then the imagery is classified using those training sites. Now there's two approaches to doing this. The first approach is to have faith. Okay, just go ahead and collect your data with whatever GPS unit you want, put it into the computer system, Idrisi, Envy, Erdos Imagine, whatever it is, and kind of cross your fingers and hope for the best results. And if you don't like the results you get the first time, try a different classification process, try different imagery, try different band ratios, and so on and so forth. That's sort of the same approach as just putting a chimpanzee on the keyboard and asking them to write a novel for you. Eventually they'll probably write a few sentences that are at least readable, okay? But that's not the approach that we want to take. The second approach is to begin by understanding the tools you're going to be using before you need to use them. And that's really why you folks are here today, to get prepped for your field season, for your data collection, and for your processing efforts. In other words, what we want to do is we want to get these systems out of the black box so that we understand them. The black box being, you know, the hidden stuff that goes on inside the software, the proprietary stuff. Understand what the heck these things are really doing. So today's topic then is we want to talk about, first of all, what is remote sensing / image processing. Give you a little overview of that. We want to talk about some geo-registration issues, why that's important. We want to talk about co-registration issues. We'll draw some contrast or describe some differences between co-registration and geo-registration. And then I'll give you a set of best practices, some rules of thumb to help you as you go through your studies. So this is just what you've always wanted. Remote sensing in a nutshell. So remote sensing is, in the most generic sense, remote sensing is learning something about an object without touching it. In the most generic sense, that's what remote sensing is. So right now, I am remote sensing or remotely sensing this desk right in front of me, looking at it, or this monitor that's right in front of me. And without touching it, I'm guessing, I'm saying to myself, I know that that thing looks smooth and it looks hard. How do I know that? From past experience. That past experience would be what we call training sites. We have previously visited that target, and we have learned by touching it, by measuring it, that that object is indeed smooth and it's hard. Okay? So therefore, when we see it again in life, we see an object that looks just like it in life, we make that instant association that is smooth and hard. For remote sensing work, actually image processing work, all of this is based upon the reflectance of that material, or the target, whatever you want to call it, and the electromagnetic spectrum, or what we call EM. Okay? The electromagnetic spectrum is shown on this slide right up here, from very, very short wavelengths through to the longest of wavelengths. And this little rainbow that you see is that very small part of the EM that is the visible part of the electromagnetic spectrum. A nice way to remember the colors associated with it, and of course it's really just a straight off gradient or spectrum across it, but we like to use the word Roy G. Biv, the name Roy G. Biv. Red, orange, yellow, green, so red, orange, yellow, green, blue, indigo, violet. Okay? And then you have ultraviolet on the other side, right out here, not visible, very, very short wavelength compared to blue. And then on the other side, we have infrared, a little bit longer, and again, outside the visible part of the spectrum. A lot of, and most of the remote sensing platforms that we make use of for range science, natural resources, do utilize blue. They'll have an independent or discrete blue band, as it's called, a green band, a red band, and then typically we'll have at least one or more near-infrared band. So, some more remote sensing basics. Okay, here's the idea. In the field, maybe we have a target that we're interested in, and that target is leafy spurge. Let's just say that it's leafy spurge. It's an invasive plant in Idaho. In fact, it's a noxious plant in Idaho. And let's say that in the field, naturally occurring, this is the response. This green line is the response of leafy spurge across this portion of the electromagnetic spectrum, from about 400 nanometers through to about 2,000 nanometers. And that's represented again by that lime green line. Let's say that the matrix, everything else except leafy spurge, is represented by this purple line. Okay? That's what's happening in the real world. Okay? So it looks like, oh, it'll be very easy to differentiate the target from the non-target, the green from the purple. When we use a satellite system, we do not have the resolution, spectral resolution, as we have seen in this green and purple line. Okay? The only satellite system or remote sensing system that comes close to on-the-ground type of spectral resolution is hyperspectral systems. Okay? These four green columns or bars that we see represent maybe Landsat imagery. Okay? And Landsat breaks down the electromagnetic spectrum into discrete bands, and that we'll call those blue, green, red, and an near-infrared. This could also be something like quickbird or spot imagery, same type of thing, a multispectral system. Okay? And then what happens is that let's say this green still represents leafy spurge. Okay, we don't see all of these little differences here. Indeed, what we see is an average. It's generalized across that part of the spectrum. So we have one response here for the blue, another response in the green, and they're a little bit different, each of the bars. Then, of course, the purple bar kind of sitting behind those green bars would represent, again, the matrix, non-target items out there in the field. And what we see now is that it's not quite so easy to differentiate the green from the purple. Maybe we could use band 3, the red band, and band 4, maybe some combination of those two bands to differentiate leafy spurge from non-leafy spurge. Now here's an idea. It would seem that if we could use high spatial resolution multispectral imagery, that we should be able to improve our classification accuracy, which is really what we're talking about is trying to see more differentiation between that green bar and the purple bar. Okay? So if we can't get it spectrally, okay, because we only have 4 bands to work with, or 5, 6, 7 bands to work with, maybe we can get it, we could improve our accuracy by simply having smaller pixels. Leafy spurge or any sort of target, cheatgrass out here in Idaho, sagebrush, how often do you suppose leafy spurge covers perfectly, very uniformly, very densely, one or more pixels? Yeah, probably not too often. Okay, what else is growing inside the space occupied by 1 pixel? There's some other stuff, right? There might be some sagebrush, maybe some other, there may be some grasses, there may be some bare ground in there. Okay. So all of those other things are what we had previously called non-target. That was the purple line. Well, if we're trying to teach the computer software, Envy, Idrisi, Erdos, that this spot on the ground right here is leafy spurge, and it is going to generalize down to a pixel at least 1 pixel. Well, if that 1 pixel is not pure target, then what you're teaching it is kind of confusing, if you want to look at it that way, for the software. Because you're saying this is leafy spurge, and maybe a lot of it is leafy spurge, but some of it's non-target, and then you go to another spot and teach it that this is non-target, another training site or set of training sites, and suddenly those target and non-target training sites look awful similar. Okay? The idea behind this statement here, that high-resolution multispectral imagery may improve your classification accuracy, is simply that if we have a smaller and smaller pixel, then it is more and more likely that our target will uniformly and densely fill that 1 pixel. Now, high spatial resolution satellite imagery, by definition, we'll say that it is imagery with less than 5 meters per pixel absolute spatial resolution. And we have to have at least, let's say, 4 spectral bands to work with. That's what makes it multispectral. On the side over there, we have a shot of some quickbird imagery. You can see we're zoomed out. For those of you who have visited the sheep station before, the U.S. Sheep Experiment Station up toward Du Bois, you'll probably recognize some of these buildings right over here. So as we zoom in, okay, with this quickbird imagery, now this is the panchromatic imagery, which is sub-meter, 0.6 meters per pixel. We're zooming right in there on their headquarters station. One other thing I wanted to mention about the high spatial resolution imagery is that right now it certainly seems that all that resolution comes at a price. Just to kind of put this into a ballpark for you, Landsat imagery, one scene will cost at most about $700. And sometimes you can download Landsat imagery free over the internet. And sometimes you can, if you're purchasing it, you can purchase it for less than $700. Quickbird, which has 2.5 meter pixels in the multispectral band, which is what we use for analysis typically, that the imagery for the exact same scene, the exact same chunk of ground on the landscape would therefore cost us $972,000 based on pricing from about 2004. So that then brings up a question that I always want to put into the students' minds, is to ask yourself when you're getting ready for these studies, really what is the imagery that I need? What is the spatial resolution that I need to accomplish my study? for some things, Landsat is absolutely perfect. In fact, some folks will say that Landsat is too resolved for their study, and they prefer to use AVHRR or MODIS type of imagery. Very different stuff. If, however, you have these very small patches of target, leafy spurge is a good example in Idaho, southeastern Idaho. Cheatgrass is a good example of that. Yes, it exists like all over the place in many cases, but it's never very dense and it's very patchy. Okay? So in that case, you're going to want to lean toward these higher spatial resolution platforms. Hyperspectral imagery, we should talk a little bit about that. Hyperspectral simply means that many spectra are sampled, and there's no cutoff line that says, once you go beyond a certain number of bands, then all of a sudden it's called hyperspectral. But typically, these systems will have 100 or more bands, or sometimes called channels. So again, we go back to this little thing that we have shown before, and we have our green target curve there, or line, and we have our purple matrix, or non-target. And what we're saying is that maybe high spectral resolution imagery can improve classification accuracy. And just imagine, if you will, that each of these columns of grid cells represents one band or channel. And what we're looking for, again, is some differentiation in a channel or in a band between the green and the purple line. For instance, this one right here. This one right here. Maybe a couple of these inside here. Advanced image classification. Because using some of these newer tools, satellite platforms such as the HiMAP hyperspectral system, we really cannot use maximum likelihood classifications, minimum distance to means, parallel pipettes, whatever, those standard classification tools, simply because those classification algorithms were not designed for that much data. We're talking about a tremendous amount of data. 3 to 5 meter pixels, 100, sometimes 250 or 255 bands, okay, over an area, and you multiply that up, how many pixels or how many pieces of data you're actually using. It's overwhelming for some of these systems that were designed for multispectral platforms. There's some newer techniques that are being used: regression tree analysis or Boolean tree analysis, spectral angle mapper, and fuzzy classification. Fuzzy classification is, of course, a soft classifier type of system. This image that you're looking at shows a leafy spurge classification using SAM, spectral angle mapper, and QuickBird satellite imagery. The red indicates places where leafy spurge is predicted to occur, and this kind of orangish color are places where the classification said that we're sure there's no leafy spurge here. It was the non-target. So, field data. Now we get back into integrating with the global positioning system. What do you think? Is field data more or less important today? We can get an awful lot of information from the satellite systems compared to years ago. I mean, QuickBird and these hyperspectral systems just did not exist 10 years ago or so. So what do you think? Field data, more or less important today? Yeah, more important. I'd agree with you. I think so. I think field data is actually more important today. Importance in the future, I think it's just going to become more important in the future. I don't mean just collecting what's out there. Okay? Well, now we have to start talking about and thinking about how we're going to collect that data to make it useful data to assist us with our remote sensing and image processing work. That gets us into the importance of geo-registration. Geo-registration is very important today. We have these field training sites, leafy spurge, non-leafy spurge, and what we need to do is we need to make sure that our training sites are placed inside the correct pixel. Okay? Now, if we're working with Landsat imagery, 30 meter by 30 meter pixels roughly, it's not too difficult to use a decent GPS receiver and feel confident that the locations that our GPS receiver is giving us will always put us inside the right pixel. When we start talking about GPS and GPS accuracy, we always want to phrase our stuff, our words in 95% confidence. We're 95% confident that our accuracy from our GPS receiver is plus or minus 15 meters or 10 meters or something like this. Okay? If that's the case, plus or minus 10 meters at 95% confidence, then we know we'll always be inside, or almost always be inside, the correct Landsat pixel. Okay? And we could accomplish that with some fairly simple and inexpensive GPS receivers. However, if we're using QuickBird imagery, 2.4 meters per pixel, or spot imagery, 10 meters per pixel, that same GPS receiver that we just talked about, plus or minus 10 meters at 95% confidence, will most of the time put us outside the correct pixel. Okay, we will not be inside the right pixel. Image georectification is super important. Okay? Today, if we're using these higher end systems like Spot, Aster, QuickBird, Iconos, and if we're doing, well, the reason why we would use that stuff is typically we have patchy targets. Then we need to make sure that, first of all, the image is in the right place in the real world. And in our experience, the imagery that we receive from the vendors is not perfectly georegistered. It may be off 6, 7, 8, 9, 10 meters, you know, to the north, south, east, or west, or a combination of that. Well, that's 1 pixel in Spot that we've shifted. That's numerous pixels in QuickBird that we've shifted. So we've got to tie that imagery down to the right place on the Earth. So we can use GPS for that. Okay? Now that's a little tricky. But what we can do with our GPS, a good GPS receiver, is to locate objects in the field that are clearly or plainly visible within the imagery. And what we've done in the past on some of this high-resolution imagery is to lay out tarps. Lay out tarps or plywood that's been painted with black and white checks, large checks on it. We put that stuff out there, stake it into the ground, make it as perpendicular to the satellite path as possible, and then when you receive that product from the vendor, you look for those things. And you know pretty much where you put them, so you don't have to scan the whole thing. And you find them and say, okay. And then when you were out in the field, you collected a GPS reading location on that ground control structure, and you know that its location was X and Y, whatever it happened to be. And if you lay out a couple of those, you can, well, more than just a couple, you lay out enough of those, you can use those ground controls to georegister your imagery and get the imagery into the right place. If you don't have that luxury of having thought of this beforehand, and I'm thinking of it for you to help you out, but if you didn't, sometimes you can use other structures that are plainly visible within the imagery, maybe some street corners, road intersections, or other things like that that you could find out in the field, and use those things to georegister. But of course, good ground controls are going to be the best thing that you could do. We can't kind of forget any part of this equation. We have to have the imagery in the right place, and we have to make sure that we have our points, our ground truth points, our training sites in the right place as well. But the other thing that you should bear in mind is the processing steps that we perform when we're taking the GPS data off of a receiver and getting it into our geographic information system. What datum is used by the GPS? WGS 84. Okay? What's the state standard geographic reference system for Idaho? Idaho Transverse Mercator, which uses what datum? NAD 83. Those are two different datums. And the fact is that WGS 84 is a geoid-based datum. NAD 83 is a spheroid-based datum. When we convert our GPS locations from WGS 84 datum to NAD 83, there's the possibility, if you use the wrong datum transformation in ArcGIS or Pathfinder Office, that you're going to introduce a lot of error. As we've seen in some cases in the past, 6 meters of error strictly because of your datum transformation methodology. So that's terrible. I mean, if you had previously collected data that was sub-meter accuracy or about a meter accurate at 95% confidence, and then you do this datum transformation to get it into the same system as your imagery, and you've just introduced 6 meters of error, well, now you're no longer co-registered, are you? And this pixel on the ground has leafy spurge in it, but if you're actually off 6 meters, 2, 3, 4 more pixels, then what was that pixel over there? Very likely in a patchy environment, it wasn't leafy spurge. So now you're teaching the computer in your image processing work that leafy spurge looks like that over there, which might have been a whole bunch of sagebrush, juniper, whatever. And then you expect high accuracy. It's not going to happen. Can we fix it? Sure. Carefully. Let's look at this thing right here, Global Positioning System Receivers. This is an ongoing study that the BLM is working on, and the source of this report is given to you right here. It's actually on the handout as well. And what we see here is they're starting off with some recreational grade receivers, and they're looking at 95% confidence, accuracy at 95% confidence in an open canopy environment, a medium canopy environment, heavy, closed canopy, and so on and so forth. Okay? Rangeline systems, I guess we get a little bit lucky. Okay, we've talked about all the stuff, oh, this is bad for us, this is bad. We're a little bit lucky because, hey, we're in the open canopy. We have the best chance to have nice line of sight with the satellites, the GPS satellites. So that helps us out. But look at what we have here, 11. The Magellan system here is about 10 to 11 meter accuracy, 95% confidence. It's okay for Landsat. You could get away with it with Landsat imagery if you're using it with Landsat imagery. Can't do it for Spot, Aster, QuickBird, etc., etc. Then they have some Garmin, some 10-meter accuracies, 4-meter accuracies. Here's a 2.5 meter. Going down here, we're starting to see some Trimbles. This is a Pathfinder Pocket. When averaging was turned on, gives them 5 meters of accuracy at 95%. Pro XR systems, the backpack type system that we have here, 1 to 5 meters. Okay? And they have some qualifiers in here. This is where PDOP was 8. That's a fairly high PDOP. Signal to noise ratio was 4 to 1. Okay? Which that's not too bad. And then we go down here and we start seeing GeoExplorer 2s, GeoExplorer 3s, getting a little bit better accuracy in some cases. But the best that we can do on this graph, or on this chart here, is the Pro XR system that gives us 1. Now, we've done some tests here in the GIS Center as well. Last summer, spent a lot of time doing some pretty rigorous tests of the GPS receivers that we have available to us. The Pro XR gave us frequently 1 meter or less accuracy at 95% confidence, and the GeoXT gives us about the same. A little bit worse than Pro XR systems, but not much. So some GPS best practices for remote sensing applications. First of all, I want to make sure that folks understand the difference between positions and points. For each point that you collect with your GPS receiver, you typically collect numerous positions per point. So a position is one estimate of where you are. And when you take numerous positions, maybe 120 or so, this rule of thumb has always been 2 minutes. Okay, so you should be able to get about 120 positions. And now with the newer systems, you can get your 120 positions typically faster than 2 minutes. That'd be 120 positions per point, and those are averaged to give you 1 point. Using real-time correctional aids. There's a satellite subscription service that a lot of the precision ag farmers will utilize. There's the WAAS system, Wide Area Augmentation system. And there's these beacons that you probably have heard folks talk about. These are real-time differential correction aids. In our experience, way up here in Idaho, we are quite a distance from the nearest WAAS relay station or control station. And when we turn on WAAS, we found that with our experiment last summer, the summer of 2004, that we actually made it worse by turning WAAS on. Why is that? How is that possible? Well, what WAAS does is it corrects for the largest source of your error in your total error budget, which is what in GPS? Atmosphere is the largest source of error, specifically the ionosphere, the troposphere. So what this WAAS system is doing is that if you think about the column of atmosphere directly above each of these ground control or these control stations, these WAAS sites, the GPS signals are analyzed as they travel through that column of air at that ground control station, or that control station, and the error at that instantaneous point in time, okay, at that column, is calculated. So what you have is you have a correction being applied to your point based on what was happening, in this case, 300, 400, 500 miles away. Okay? So in our study, we found that turning on WAAS and taking that WAAS signal actually reduced our accuracy. And that's simply why, because you were correcting for atmospheric phenomena that were happening 300 miles away, not what's happening here. It's a great system if you're close enough and your conditions are similar enough to what's happening over there. Really nice. Okay? In any event, we always want to establish the best baseline possible, best baseline that we can. So if we, for sure, we want to average, get 120 or so positions per point, and if we're close enough, let's try to use some real-time correctional aids. That establishes a good baseline. All that baseline stuff happens in the field. Once you say, I'm done, close up this rover file, close up this GPS file, then all the work that you've done for baseline is finished. It has to, that's all stuff happens in the field. Then you come in to the office eventually, and there we want to use post-processing differential correction. Okay? There are now, right around here, numerous community base stations that you can use to download base station data that can be used to differentially correct your data. We know the location of that GPS antenna. It was originally surveyed in with a real-time kinematic survey-grade GPS receiver. That was then verified or validated by surveyors, licensed surveyors here on campus at Idaho State University. So we know where that antenna is located. We know its X, Y, and its Z, its elevation. So that thing is constantly downloading or acquiring GPS files, and each time it receives a position, that position may change a little bit. Okay, at one point in time, the GPS, our community base station may be told that it is 2 meters to the west of where we said it was, where we know it is, and maybe it's 5 meters to the north. Well, that's excellent information, because whatever's happening right there up on top of Gale Life Sciences in Pocatello, Idaho, is probably very, very similar to what's happening just 20 miles away or so in the Snake River Plain, very, very short distance away. Very, very similar atmospheric conditions and same column of air. So we apply, and this is very much in a nutshell, we apply that same error to your GPS locations, the stuff you guys collected in the field, and then correct your data so that it's much more accurate. It's not going to be, the GeoXT is not going to give you, in most cases, centimeter grade accuracy. You may luck into it sometimes, but for the most part, the GeoXT that you folks are going to be using will give you plus or minus 1 meter, or a little bit less than that, even 3/4 of a meter at 95% confidence. What accuracy is required of your GPS points? So here you got to start thinking once again about the imagery. Okay? I'm never going to tell people, yeah, just be sloppy, who cares? Okay? You always want to do your best and get the best locations that you can. But I'm also not going to tell people if they had to invest in a survey grade system and lug that big thing around for centimeter grade accuracy when what you're using is maybe spot or aster imagery. That, as we have just seen, GeoExplorer 3s, GeoXTs, and ProXR systems will all work just fine for you. A rule of thumb, when we're talking about the accuracy required of your GPS points for remote sensing, the rule of thumb is we look at 50% of the size of a pixel in the imagery you're going to be using. And here we're talking about the absolute spatial resolution. So 2.4 meters per pixel on the QuickBird multispectral. We apply this little rule of thumb to it. We're at 1.2. 1.2 meters at 95% confidence is what we need. Know what receivers will produce these results and then use the appropriate receiver.